Okay, in this slide, we have a summary of these right-hand rules that we talked about. So the first right-hand rule that we talked about was the one that we used to get just the direction of the magnetic field. We talked about it briefly and we didn't use it much. Okay, we just, what we said, we use the thumb to follow the direction of the current, and then our four fingers grabbing this, encircling this wire to give us the direction of the magnetic field. No? So the magnetic field are these circles around the current. That's it. That's all we talked about. We didn't use it much. That's what we are going to start doing now. We are going to start playing more with this rule. Okay. The other rule that we talked about was the right hand rule, the second right hand rule that we use to get the force on a current because due to a magnetic field. The book is calling the one for the charge a third rule. It's not, okay? These two are the same. This third drawing here is the case that we discussed when we have a single charge. But as we said, if this single charge is positive, everything is the same as we did for the current. Now, the only thing that now our four fingers will be following the direction of the velocity of that charge, but everything else is the same. The only addition to this story is if the particle would be negative. Now, if it's negative, we do everything that we did for the positive charge, and then at the end we say, okay, but now I have to switch, I have to flip the direction of this force because I'm talking about a negative charge. Okay, so basically we have just two rules. The one to get the magnetic field once we are giving a current, and the other one to get the force on a current due to a magnetic field, or the force on a charge, moving charge, due to the magnetic field. Okay, what we are going to do from now on, we are going to play a little bit more with this equation here, with the idea that around a charge, around a current, we create magnetic field. So that's what the next slide is about. This rule gave us the direction of the field, but we never talked about the magnitude of this field. So what is the equation that determines the magnitude of this field? This is the equation. This mu naught here is just a constant. No, just as when we were talking about electric field, we had that K that was just a constant. Okay, so we have this mu naught, which is just a constant. In the case of the electric field, we talked about K or about the epsilon naught. No? So just a constant. It's a constant, which you don't need to know. It's written here, divided by 2 pi, okay? And then comes what is important. This magnetic field is directly proportion to the current. The bigger the current, the bigger the magnetic field that it's going to generate. But this magnetic field is inversely proportional to the distance. The distance from what? The distance from the wire. Of course, the further away I go from the wire, the smaller this magnetic field will be. But you see that there is something interesting in this story. Now, when we are talking about electric field, we said that the electric field was proportional to the charge, okay, but inversely proportional to the distance square to this charge. Now, the magnetic field is not the distance square. We have that the magnetic field is proportional to the current, but inversely proportional to the distance, not squared. Okay? Very well. So this is the equation that we need to solve the problem that is coming next. So what is the problem here? We have a wire carrying current. This current is going up. We know that it's going to create a magnetic field all around. So what is the direction of this magnetic field? You can do this as an exercise. Well, it's going to be encircling this wire. In front of the wire, this magnetic field is going to the right, gets into the page, now on the right side. Behind the wire, it goes to the left. On the left side of the wire, it comes out of the page. So we have these circles around this wire. And we have small circles and we have also big circles. The further away we go, the smaller the magnitude of this field. What they want to know, what is the information that they give us? Well, they say that this current This current is 25 amps, and they want to know what is the magnetic field at this point here, at this point P. There is nothing at this point, now it's empty space, but because of this current, we will create a magnetic field, which there is a value for this magnetic field at this point P. What is the value? Well, what is the distance from the wire? The distance is 10 centimeters, so 0.1 meters. So that's it. We just have to enter these values in the equation for the magnetic field, putting also this constant, and you will see that the value of this magnetic field is 5, 10 to minus 5 Tesla. Remember, Tesla is the unit for magnetic field in the international system.